Hello, my name is Theo DeGuzman.
I'm Leen Alfaoury.
I'm Xander Song.
We're a class of 2024 mechanical engineering students at Johns Hopkins University, and we will be presenting our research project for Mechanical Engineering Thermodynamics Laboratory.
The goal of this project was to test a commercial product and determine its thermodynamic efficiency. The product was required to operate over a variety of conditions and cost less than $30.
We chose to do a water gun due to its simple design but multiple energy conversion processes. When the user operates the device's pump, the pumped air pressurizes the tank that holds both the air and the water. Then the trigger is pressed and a valve opens, allowing the pressurized air to expand and shoot the water out.
Energy is input into the system by pumping air, which can be measured as a force times a distance. A slide potentiometer and a load cell attached to an Arduino measured these values.
The next measurable step of energy transfer is the boundary work being done by the air as it pushes the water out. The tank's pressure was measured by the pressure sensor and the volume can be calculated, allowing the Arduino to determine the work as pressure times the change in volume.
Finally, the energy output was the kinetic energy of the water. We directed the water into a container being weighed by a load cell. Knowing the nozzle diameter, the Arduino could determine the mass, flow rate, and velocity. From these values, the total kinetic energy output could be determined.
The efficiency would be calculated as the energy output divided by the energy input at each step. We tested the water gun in experiments that changed the number of pumps, the angle at which the gun was held, and the amount of water in the tank initially.
Notice the testing rig created to hold the water gun and the Arduino mounted to the setup and the computer reporting data in real time.
In every trial, the water gun would be emptied and refilled, set to the correct angle, and pumped to the desired number of times. We would then hold down the trigger until water stopped flowing and save the results recorded.
The results of the experiments showed optimal operating conditions where the water gun worked at maximum efficiency. The ability to measure an intermediate step in the process also helped us more thoroughly understand where the losses were occurring in the system.
We found the optimal number of pumps to be approximately 30 pumps, the optimal angle to be 15 degrees pointed downwards, and the optimal amount of water in the tank to be about 400 millimeters cubed or about 3/4 full.
These results appeared fairly consistent across trials and did show significant changes over the range of operating conditions. Therefore, this experiment was designed and conducted successfully.